were argued and proved. Where proof is required, where proof has a deficiency, where the arguments are not complete, and so on and so forth. Okay. So going through these things is a good mental exercise in mathematical arguments. Okay, the idea was we have two cardinals, we want to add them, we want to multiply them, and we want to look at the power function. Okay, so let's say let A and B be any two cardinals. Last time towards the end I said what is A plus B and what is A into B, but I'll now start with those A plus B again and then point out a few things. So first of all, how do we define A plus B? Okay, so the idea that we had in mind was take a set with cardinality A, there is a set another one with cardinality B, make them disjoint and then look at the union. Okay, so let's write that down. So there exists sets A and B such that the cardinality of A is A and the cardinality of B is B. Let me write it, doesn't matter, A or B or X or Y, doesn't matter. Okay. Notation should not be a problem. We should not get bogged down by notations. Okay, the idea should be important. Okay, so A and B may or may not be disjoint. So what we do is first we extract disjoint set. Okay, I will write the full argument and then ask some questions. Okay, so let X and Y be sets defined as follows. Now, before I do that, I will make a statement that without loss of generality, let's assume both are greater than or equal to 1. Because if one of them is 0, that means you are simply adding nothing. You are just putting an empty set there. Okay, so without loss of generality, this is a very dangerous word. Okay, without loss of that also they write it in short form. Mod A, mod B greater than current. A, B greater than. Okay, we are going to now define two sets X and Y starting from this A and B as follows. Because there are at least one element, there is at least one element in A. Okay, so let A naught be a fixed element in A. Then define X to be equal to A, Y to be the set of all A naught B where B belongs. I should not use B, but anyway, I use B for something else. Okay, then clearly the cardinality of X is A, the cardinality of Y is B, and X and Y are we define A plus B as A plus B definition of the cardinality of okay. Now, how do you feel about this definition? Uncomfortable, comfortable, satisfied, not satisfied? pretty careless. There's something that's bothering them, that definition. So this is the type of questions that you should be asking when you are doing something new. What do you think is mathematical object or raise doubts or questions about this definition? Anything comes to your mind? I don't care what B has, but as long as B has, I am only doing, take the B and put some kind of an envelope to it, A0. The same envelope. I put every element in a 4 by 9 envelope. That's all. Nothing happened. The set X may have a element A0 comma B, then that this would have become A0 comma B. A0 is a fixed element. Some one element in A I pick. Any element. Even, okay, go on raising all the objections. See, A and B are, the idea of cardinal, some of the questions he raises are valid, okay? I am just writing them loosely. The idea of cardinals is a abstract thing. To define, you are coming down to the concrete level and taking representatives. The set A, the set B, the set X, the set Y, etc. Okay? So, what is the guarantee that if somebody else works with some other representatives, he is not going to get different results? In other words, this whole definition goes through some representative sets A, B, X, etc. So we must show that eventually this definition is independent of the choice of these sets. So basically, therefore, trick proof will say, given two cardinalities, there exist two disjoint sets A and B, that the cardinality of A is A, cardinality of B is B. Then we define the cardinality A plus B to be the cardinality A union B cardinality, and this definition is independent of A and B. If you have taken a C and D, still the same thing you get. So such sort of logical small points you have to take care, but all these can be taken care of. That's what I want to say. Okay, so even slight questions like that he asked have to be settled here. Okay, so basically, therefore, this definition has to be formally given as, given any two cardinalities A and B, there exists two disjoint sets X and Y, that the cardinality of X is A and the cardinality of Y is B, and A plus B is defined to be this, and if X1, Y1 or any two other disjoint sets with X1 is equal to A, mod Y1 equal to B, then mod X1 union Y1 will also be equal to mod XU Y. This is all the process that you have to go through in this definition. All this can be done, and therefore the definition A plus B comes. Is that clear? So there are a lot of small things that we have to fix, okay? It is just, it is not a complete definition. One has to settle down all small points. But intuitively, this is what you do. The moment two things are given, there are always the concrete avatars of this which are disjoint, and you take the union and if you take any other two of that, they will give the same result. How do I define product? Both are? Yes. What is the power set of the null set? 1. So you take two disjoint singleton sets. Okay. This. Okay, I will leave it to you to fix all these points. All these can be fixed. Now that you are asking questions, you are asking the right questions. Therefore, you see there are technical difficulties, but what I am saying is all that can be fixed, and we can make a final statement that given two cardinalities and be greater than or equal to 1, you have two sets x and y which satisfy these properties, and we define this to be this, and for any other x1, y1 with this property, you will get the same result. That's what the final answer is. Okay. As I said last time, you have to go on questioning yourself about these cardinals to get final pick. And every time, best thing is to write your own proofs. Only when you write your own proofs, you see the difficulties. Let me sit down and try to write it. What happened? Oh, here I have some difficulty. What happened here? I have to go back and see. So it's not something which just gels immediately. Every now and then, all kinds of doubts come into your mind. I will raise some more questions like this. And A and B is simply defined to be, here I don't even bother about disjointness. Again, I have to show that if A, instead of A and B, I had chosen a A1 and a B1, then the cardinality of A1 is A and cardinality of B1 is B. I will still get the same result. These are things which have to be settled. That this is actually not getting to get sucked into too much discussion on this. So that's roughly the idea. Okay. But more importantly, I am going to discuss the so-called power. I want to discuss P power A. Now, why I didn't write A power B, it doesn't matter, both are same. The B is used as base and A is the exponent. That's why I put the B there. And it's convenient to write. So, how do I define such power functions? That's the fundamental question. Okay. And this is going to be very useful for us. So, whenever we are in trouble, we go back to C and go to finite sets and see what happens. Okay. So, suppose I have a set A n elements and B with m elements, and I look at functions from A to B. Okay. I look at functions from A to B. How many functions will be there? M power n. So all the computers. So now I am going to look at this notation. FAB is the set of all functions from A to B, and as I said, there are total number of functions is m power n, which is m is the cardinality of B and is the cardinality of A. So this is what suggests how we are going to define these exponential functions. Okay. So now let's say A, B are two cardinals, and I want B power A. So I must make this B as the cardinal. I must get a representative set for this B, and I must get a representative set for this A, and look at all the functions from A to B and find out its cardinality. So what you do is, by definition, this is the collection of all functions is cardinality, where A and B are any two sets with cardinality of A as A, cardinality of B as B. So this is how I identify. Now this now is everything in terms of set theoretic language, so immediately it gets carried over there. Mod B power mod A. Now I have chosen B to have this B. So this A is this A, so it becomes B power A, is defined to be FAB. The collection of all functions from A to B and that cardinality. Okay. Now again, we have to make sure, assert and prove that if we had chosen a A1 with cardinality A and a B1 with cardinality B, and look at all the functions from A1 to B1, that will also give the same result. That part we have to assert. It is independent of the choice of A and B. Now I am going to look at this collection a little bit carefully in various formats. Okay, this particular aspect. There is a lot of dusters here. I will reduce to one. There's some problem with this. This is probably the whiteboard duster I used to here. Yes. The whiteboard duster is near the blackboard, and the blackboard duster is far away from it. Next time somebody uses this, it will be in trouble. Okay, so now let's look at this a little bit carefully. Let us take some special situation. Okay. Let us take A to be the set of natural numbers, okay, and B to be our binary. That's why I use the B. So, what is mod A? The cardinality of A is what we called as Aleph naught, the countable infinity. And the cardinality of B is the two elements, is a finite cardinality. Okay. So, mod B power mod A, which is the same as 2 to the power of Aleph naught, that by definition is equal to the cardinality of all the functions from A to B. Right? Collection of all functions from N to B. That is what 2 to the power Aleph naught is by definition. Okay. Now, do you remember this fellow? The collection of all functions from N to B. Is the collection of all infinite binary strings, which we saw last time, and it is uncountably infinite. So it is equal to B, the collection of all infinite binary strings, and therefore 2 to the Aleph naught is strictly greater than Aleph naught, which is uncountably. Okay. is uncountably. Yes. Say that again. All the okay. No, there is no question. All are infinite length. It's from n to b. F1, F2, F3, F4, F5, F6, etc., etc. Everything is an infinite string. It's not by length. Okay. It is not infinite strings of finite. It is not binary strings of finite length. See, every element here is a function from n to b. F1, F2, F3, F4, etc., etc. Each one of them is either a 0 or a 1. So when you write the full function, you will get an infinite string of zeros and 1. Okay. Right. So the collection of all infinite binary strings. It is not the infinite collection of binary strings. The collection of infinite binary strings, which we saw last time. Okay. And it's uncountably infinite, and therefore LF naught is less than 2 to the LF naught. Right. Our definition, because of our definition of the exponential. And we also saw, I should not write B, the cardinality of B. And we also saw this is the collection of, what is that? This was the equivalent to the collection of all decimal expansions of numbers between 0 and 1, which involve only 3 and 7. So all these are equivalent. I will leave some space here and write more. So I am going to do some random things and confuse you as much as possible, so that you start thinking. When you start, when you sometimes you are okay, you control from digression. Let me reverse the rules for the time being. Okay, I am going to observe something else. So now I am going to take say a set B power of 2. Okay. There's going to be a lot of confusion about this also. We'll resolve some of the things. By definition of the exponential function, what is this? Okay, let me not even, let me do a little bit more general thing than this. Okay, that probably is worthwhile doing it. We'll be using it later. Okay. So let us analyze this FAB a little bit more carefully. The collection of all functions from A to P. Now forget about all this analysis course and things like that. We were taught to begin with, where the things were less confusing. Whenever you gave a function f of x, you take a graph sheet and plot. Right, what did you plot? It's called graph sheet, and something you plotted. What did you plot? Some points. What were these points? I took the value of x and point the value of the function and put that point in the graph sheet. That point had coordinates what? X and fx. And that is called the graph of the function. So with each function, so for each f, so for every such function from A to B, we define the graph . GF of F as GF, when it dropped the comment, it took all these points. So, it is a collection of all A, FA as A varied over the domain set A. The collection of all those points was eventually the graph. Draw the graph. Whatever that means. We were very innocent. We took the word for granted. He said this is how it should be drawn. We drew it like that. Okay. It is simply collecting all those points, the domain value and the function value at each point. See, it can be drawn in a graph, it can be written in a tabular form or whatever it is. In the case of when we are doing an experiment in the lab, you put the various time points and corresponding temperature or something like that. And then later you went to the graph sheet. Both are same. Okay. So that table AFA, that full data is called the graph of the function. So for every function, there is a graph associated, the graph of the function. Okay. Now, what kind of a gadget is this graph? No, for heaven's sake, don't bring graph theory here. Okay. We are talking set theory. What sort of set is this? Where does the set live? Where does the set live? A cross B. This is a subset of A cross B. It's an ordered pair. The first element is from A. The second element is the value of the function is in B. So it's a collection of points in A cross B. So it's a subset of A cross B. Am I right? So it's a collection of, see, every point inside is a point in A cross B. So it's a collection of points in A cross B. So therefore it's a subset of A cross B. So for example, if you take the graph sheet, that is the line cross line. In that, the graph is a collection of some points in that plane. Okay, that's a subset of the plane. In this case, the plane, the x-axis is A and the y-axis is B, and the graph is a subset of that plane A cross B. That's all. Okay. So the graph of any function from A to B is a subset of A cross B. So I can also write it as it's an element of 2 to the A cross B, right? 2 to the A cross B, the collection of all subsets of A cross B, and this is one collection of subset of A cross B, one subset of A cross B. So it's a subset of A cross B. The elements of this are subsets, this is one of them. So the graph of F is element of the power set of A cross B. If you take a function from A to B, for any function, the graph of F is an element of the power set of A cross B. Is that clear? Now, if you drop a function f of x equal to sin x between 0 and pi by 2, and f of x is equal to cos x between 0 and pi by 2, the two graphs are different. Different functions have different graphs. If f1 is not equal to f2, then the graph of f1 is not equal to graph of f2. At least at one point there, the values must differ. So if f1 is not equal to f2, f1, f2 in FAB, f1 implies graph of f1 is a different set from graph of, the plot will be different, common sense. Okay. There are two functions and you plot. If the plot is the same, the two functions are the same. So the plot is the same if and only if the two functions are the same. So now with each function f, I have a uniquely identified graph, and this uniquely identified graph is a subset of the Cartesian product A cross B, and this uniquely identified graph is an element of the power set of A cross B. Okay. So now what I do is collect all such graphs. For every function I have a graph, collect all such graphs. Okay, that is a set. So many sets will generate. Now where does this set live? Where will you pinpoint this to be? Forget about this first and see where is this fellow. That fellow is in 2 to the A cross B. And now I am collecting several fellows in 2 to the A cross B. So therefore he is a subset of 2 to the power of A cross B. So he is contained in 2 to the A. Let me call it as K. Okay. Yes. Wait for 1 minute. Okay. And wait for 1 minute. Later, wait for probably 1 month. You will get several clarifications for your question. Okay. Right now, wait for 1 minute. A partial answer to your question will come. Okay. So K is part of 2 to the A cross B. Okay. Some of the questions I will immediately answer after finishing this. Okay. Certainly I will answer your question. So now what have we done? I have FAB, I have K, which is a part of, okay, I don't know whether it's equal. I'll safely put subset are equal to. And now, with each fellow here, I found a code here. What is that code? The graph. The function is coded by its graph. Each function has a code in K. Different functions have different codes. And now the way I have collected this GF is on true. Because this K is only from the graphs of function. So therefore, this function phi mapped from here to here defined as phi of f is equal to GF is 1 1 onto map from FAB to a subset K of 2 to the A cross B. Is that statement clear? So I have, let me draw a picture. I have this FAB. Let me draw here, that is. Okay. I have this, what I have done is the following. I have this set FAB and I have this set 2 to the A cross B. Inside this I have this K which contains all the GFs. All the GFs are sitting here. And now F2 GF is the phi function. And therefore this fellow is equivalent to K. So what does that statement say? FAB is equivalent to a subset of the power set. And therefore the size of FAB can be at most the power set of 2 to the A cross B. Okay. So therefore the cardinality of FAB is at most less than the cardinality of the power set of the Cartesian product. We will make many more statements about it, or you can make many more statements about it. All I want to show is that it is at most this. You may sharpen that result, you may improve that result, etc., etc. At the moment, I have got only this. So let me note that result also so far. So far we have got, one was this, aleph naught. The first result we proved was aleph naught less than 2 to the aleph naught. And the second result here is the cardinality of FAB is at most the cardinality of. So now that I have written it, I'll come back to your question. With each function, there is a subset associated in A cross B. I am not saying every subset is associated with a function. Okay. So there may be some subsets of A cross B which are not at all graphs. Only that part I am going to identify. Okay. Now we may ask whether it is equal. What are the other things happening? I am not going to worry about it. At the moment, I will only worry about the fact that it is at most 2 times A cross B. Is that clear? If not clear, I am very happy, because it will bother you all night. If a problem bothers you all night, you are in the right track. And if it doesn't bother you all night, either you are not in the right track or the problem is not worth looking at. And if it's not bothering you, if it's very clear, I'm happy, because finally I succeeded in explaining it to somebody. Okay. So either way, I'm happy. Okay, whether it's you agreed or you don't agree, or clear or not clear, I'm quite certain. Okay. So now take these 2 points. Aleph naught is less than 2 to the aleph naught, and the cardinality of the set of all functions from any set A to B is at most the cardinality of the power set of A cross B. The third point, a simple point I will ask, is the following. Suppose I take n, A to be n, and B to be 0, 1, and then I look at A cross B. What can you say about this cardinal? Very clear. Am I clear? I take the set A to be the set of all natural numbers, and I take the set B to be the set 0, 1. These will all be exercises in some book. Okay. It can be easily proved, it's trivial, it is obvious, etc., etc. So some of these trivial, obvious only I am trying to throw up here. What common sense tells you? See, I have one string of n's and another string of n. n0 and n1, where n runs through the integer. So the total is about union of n zeros and n ones. How big is that? 2n. What is 2n? You are in a very strange arithmetic. 2n is n. I remember last year I met a kid who is in the 9th standard. He asked me, what do you teach in higher mathematics? I told him, see, in school we teach 2 plus 2 is equal to 4 and 2 into 2 is equal to 4. In higher mathematics we say 2 plus 2 need not be 4 and 2 into 2 need not be 4. So then he said, if I want to go to higher mathematics, then why do I learn lower mathematics? Because you are going to anyway say that's not true later. Okay. So I had no answer for that guy. But anyway, so this, see, what is this? This is the collection of all n zeros and n ones where n belongs to, you agree? Either n zeros or n 1. The second coordinate can be either 0 or 1. Okay. Now what you do is take all these fellows and map them to even, and take all those fellows, map them to odd. So map this fellow to 2n minus 1 and map that fellow to 2n, and you will have 1 1 on to map, and that will be precisely n. Map the n zeros to 2n minus 1 and map the n ones to 2n, you would have covered the integers in a 1 1 on natural numbers. So the cardinality of this is precisely Aleph naught. So 2 times Aleph naught is Aleph naught. In the infinite case, 2x equal to x, therefore x equal to 0 is false. That's why Cantor was considered a mad fellow. He is simply destroying all the faith that we had in mathematics. So Aleph naught times 2, the cardinality of n cross b is still the cardinality of n. Let me, this is something like probably eventually the type of result that will come out, the infinities, is somewhat similar to, probably if my understanding is correct, the idea of Turing machines. You put several Turing machines together, you will still get only a Turing machine. That's what it is. It is not 4 Turing machines, it is a bigger Turing machine. It is still a Turing machine. Turing machine plus Turing machine is a Turing machine. So Aleph naught plus Aleph naught is Aleph. So if you want to go, if you want to raise it, you must bring somebody more powerful. Okay. You cannot raise Aleph naught to higher level until you bring a higher fellow at the multiplication. So, but basically at the moment, just we will observe this fact, that the cardinality of n cross b is still the cardinality of this. On the other hand, I will now use that result here. Therefore, the cardinality of the set of all functions from this n to this b is equal to the cardinality of n times 2, which is the cardinality of, because n cross b is n itself, the cardinality. These two sets are equivalent. So it is simply 2 to the n. Okay, but the cardinality of this is 2 to the, cardinality of that is 2 to the Aleph naught by 1, by our earlier result. Okay, so 2 to the Aleph naught is less than or equal to 2 to the n, and by 1 I have this finally. Okay, Aleph naught is less than 2 to the Aleph naught, less than or equal to the power set, the cardinality of the power set of n. Now what can you conclude? Continuum hypothesis says there cannot be an infinity between this and that. Therefore, equality must take place. Because if equality doesn't take place, we would have got an infinity which is bigger than Aleph naught but less than 2 to the n. And continuum hypothesis asserts this is what Cantor wanted. Okay, CH says that 2 to the Aleph naught must be equal to cardinal. Looks like consistent notations. Therefore, we wanted the consistency notation, and that's what comes to the continuum hypothesis. There. So you take 2 and raise it to the power Aleph naught with our definition of exponential that rightly coincides with the notation of the cardinality of the power set. And this would not have been possible if we did not have continuum hypothesis. We would have been stuck. We don't know how to prove the equality. So that's where Cantor wanted the continuum hypothesis. Okay. Probably a two-line proof will do with it, Stromberg or something. If you see, you won't even notice it when you're turning the page. Okay. Basically, most of it said it's very easy to see that. So it's very easy to see that, provided I spend 45 minutes or 50 minutes on that. But even probably still there will be some doubts hanging in your mind. But the fact is, this is precisely where one of the reasons why Cantor brought in his Cantor continuum hypothesis, put that equality there. Otherwise, you would have ended up there will be a bigger mess of infinitives. Okay, what does that all lead to? Okay, let's see what. Yeah. Here, this was B to N, is it? Okay, doesn't matter. That's what the notation is. Basically, I write as three facts together, you will get this. Okay, now my main question is the following. So all these, you put all these things together, continuum hypothesis, you get 2 to the left naught is equal to 2 to the n. Okay. Okay, I'll put all the details in that. Yes. B to the, I'm not able to hear. The number of functions from B to N is different from N to B. Whichever one I use there, put the right one, you get the answer. Okay. You don't worry about the notation. The idea is this, okay. One of them gives this, okay, and that gives this. Therefore, put continuum hypothesis. You get what you want. I did both FBN and FNB. Okay, so one of them will fit into this. I have this result. This is what you have to do. And if you did not want it, I put it this way around. Okay. The idea is that. Okay. Right. Okay. So now we are going to still all these because we don't know what numbers are, but anyway, natural numbers are. Let me go on making intuitively many things. Okay, so now we had the collection of all infinite binary strings. That cardinality was the same as the collection of all numbers between 0 and 1, whose decimal expansion involved only 3 and 7. And these were all uncountably infinite, and eventually therefore we get this is equal to, this was 2 to the left naught, okay, the set of all functions from n to 2, and this is less than or equal to the cardinality of all the numbers between 0 and 1, right? Because D37 is a special collection of numbers between 0 and only those which involve 3 and 7. But the 0, 1 may have other numbers also. So this cardinality is at most this. Now I will do a very quick cheating, removing certain technical details. But every number between 0 and 1 has a binary expansion. And therefore it will be identified with that. So there will be an equality. Every number between 0 and 1 has a binary, what do you call it? Binary expansion. We'll call it only that. Like decimal expansion, a binary expansion. And therefore, every binary expansion will correspond to a number between 0 and 1. There are small technical difficulties, but that can be sorted out. But eventually, therefore, our cardinality of the interval 0 to 1 is 2 to the left naught. This we will denote from now on. This is called the cardinality of the continuum, therefore it is called C. And that C is written in a very peculiar manner, which I will not write, because my handwriting is already peculiar. Right, that's how it is written, in very small letters. Right. So therefore, all the numbers between 0 and 1 have the same cardinality as the power set of n, which we denote by 2 to the n0, and also from now on as C, as the power of the continuum, the size of the continuum. Now, some very, very strange things happen. If you take 0, 1, the power of the interval, open interval 0, 1, and for, as they say, a topologist is one who does not know the difference between a car tire and a donut and a budil vada. All are equivalent for it. Okay? They are surfaces with genus 1. That's all you know. It's called torus. Okay? Like that, a set theorist is one who doesn't know the difference between 1 mile and 1000 miles. Okay. So what I mean is, you now take any interval AB, not necessarily 0, 1, it may be minus 250 to 342 or minus 0.001 to 0.00001. Take any open interval, any interval between A and B, and these two are equivalent. As a set of points, these two are true. So if this guy goes and asks for 1 meter of cloth, and the shopkeeper give him 1 centimeter of cloth, he won't know the difference. The set theory. The same parameter, the same number of points are there. So the idea is the following. See, after all, we keep a magnifying glass on this, which magnifies it, and then identify point to point. They are equal. So what is the map that does it? One map is B into x minus A plus A maps 0, 1 to AB. When, no, the other way around, AB to, what is that map? When x is equal to A, it must be 0. When, let's put it other way. I want 0, I want to go to A, 1, I want to go to B. So it is the slope of the line is B minus B by A, is it? B minus 1, B minus 1 by A. That's what that term is. Into X. What is that map? Linear map, okay? Forget about it. You draw the line 0 to 1. At 0 it should be A, and at 1 it should be B. Draw that line, okay? Draw the equation of that line. That maps 0 to 1 to A. The height is A, and this height is B. That straight line equation is a map that maps 0, 1 to A. So therefore, it doesn't matter whichever interval you take, 0 to 1 or 0 to 100 or minus 1 to 1, all of them have the same cardinality, the continuum. So the continuum is the fact that there is an interval. That is what a continuum is. Okay. There is no gap. That's what is the final non-gap. There is no gap there. Now we can stretch it further. You can make it an infinite interval also. 0 to infinity also. A to infinity also. 10 to infinity also. Minus infinity to infinity. So the 0, 1 is equivalent to any open interval, finite or infinite. So therefore, the real line, the cardinality is C. That is the cardinality. To the other. The cardinality of R is 2 to the left knot, and which is equal to the real line is essentially the power set of the integers. Okay, and that's where Kronecker's famous statement, God gave us the integers, everything else is my own work, man's work. He gave me those positive integers. I constructed the real numbers as a power set of the positive real numbers. So it is an amazing thing that just from the positive integers, you could construct everything, right, all the way up to the continuum, okay, by a theoretic language. And Cantor went one step further, and he said, why do I need all the integers, positive integers? I will construct them myself. You just give me the empty set. Okay. So then I say 0. Then 1 is the empty set. Its cardinality is 1. And this is 2. And now go on, I construct any positive integer. And therefore I constructed the real numbers. And so Cantor said, God gave us nothing, the empty set. Everything else is man's work. So that is an axiom in set theory, that there exists empty set. God gave us nothing. That's one of the axioms. There exists empty set. It is not there, the whole thing is chaotic. That there is an empty set is one of the axioms. Once you have that, Cantor said, I don't need anything else. I'll construct everything. The real numbers is simply I'll construct positive integers first, and then look at the power set of it, how do I construct it. This is one way. I will look at the real numbers in different ways as we go along. Okay. So therefore, one of the most important things in this whole analysis that of looking at the power set, etc., was the cardinality arithmetic, was to come to this continuum hypothesis stage and identify 2 to the left knot to the power set of it. Any questions? Yes. Okay, I probably might not. Which one? Okay, let's go back. What was B? I don't remember which notation I used. Where? This one? Where is it? Here? B, first of all, B is a collection of various ways. A1, A2, A3, where all the edges are in 0, 1. Right? The string of length infinite, unending binary string. Look at all possible such strings. This can be thought of as a function from every such binary string is a function from n to 0, 1. F1 is A1, F2 is A2, F3 is A3, F4 is A4, and so on. From where to where? That's what there are some technical difficulty, technical things you have to sort out between 0, 1 and identification of B. Remember I made that statement, I gloss over that. Those can be, you decide on certain type being thrown out, namely like either the non-terminating or the terminating, repeating, etc., etc. Certain technical arguments are missing there, but eventually you write it. That's what I meant. So I am going to gloss over that. I said I would do a bit of cheating. You caught me. See? That's all. That bit of cheating has to be sorted out here to show that this is equal to that. Yes, true. That's true. There are difficulties there. Because there are some numbers which will have 2 possible binary expansions. You must identify what type of numbers are those, sort them out, and then do this. Yes, you are absolutely right. Okay. So the moral of the story is the real numbers is equivalent to the power set of A. And that is the next infinity level after the positive integer. After the positive integers, the next infinity level is this, and that is precisely the real number. That's precisely the collection of real numbers. And then subsequently will be the power set of the real number, power set of the real number, power set of the real numbers, and so on and so on. And we'll identify those things also. It's very important to know these things. Some of these theorems involve these. One more point I want to make is just for you to think. Okay, suppose I have a cardinal number. Okay, now I have defined A into A. How did I define? This is the cardinality of A cross A, where A is a set with cardinality A. A into B was the cardinality of A cross B, where A has cardinality A, B cardinality B. Now I am taking both A and B the same. So A into A is the cardinality of A into A, where the cardinality of the set is the little a. Okay. And how do I define A squared? This is an exponent. So this I should define as, according to my definition, is the collection of all functions from 0, 1, right, to the set A, where mod A is where mod A is. Correct? Now I would like this to be also, after all 4 into 4 I call 4 squared, right? So I would like to call A into A as A squared. Now, but A squared I have defined it this way. Will these two be the same? Okay. Otherwise, there is a terrible notation, right? And luckily they are the same. Try to convince yourself that both will be the same. That is, the cardinality of this will be the same as the cardinality of this. Well, probably I could let me see whether is it either. That's a question. That has to be settled, right? Whether these two will be the same. If they are not the same, we are using horrible notations. A into A need not be A squared. I think old students already have run away from maths. Whoever is remaining will also run away from maths. That's not going to work. Okay. So we have to convince ourselves those things will happen. Okay. And the arithmetic of cardinals takes care of all these things. There are many things that we can prove. First is the law of trichotomy. That is, if A and B are two cardinals, A less than B or B less than A or A equal to B. One of these three must hold. I already discussed this when we discussed the Schroeder-Bernstein theorem. The second thing is, if A is less than or equal to B, B is less than or equal to A equal to B. That's what Schroeder-Bernstein theorem is. Okay? Schroeder-Bernstein theorem precisely says if A is less than or equal to B and B is less than or equal to A, and then A equal to B. And a very then A plus D is less than or equal to B for any other cardinal D. We add same quantities in Euclid's language, equals added to unequals, the unequals will remain unequals. It's very interesting to read Euclid because it's all written in verse. Okay. And again, all the standard laws, A plus B is B plus A, A into B is B into A plus B plus C is A plus B plus C. All this can be proved, and then A into B into C is equal to A into B into C. The distributive laws, A into B plus C is A into B plus A into C. All this can be proved, okay, with respect to the any cardinal number. They are finite or infinite cardinal. But what is important is the following. Suppose you add two cardinals. I am not going to prove all these things. Some of the proofs involve more things that I have to do later. Okay? So it's not, for example, the convincing of this, that result I wrote somewhere, that these two are equal. Remember A squared and A into A. Those two are equal. The most general case will involve axiom of choice, Zorn's lemma, etc., etc. Okay? It's not easy. That's why I didn't do. You have to convince yourself. Now A plus B. Suppose you are given two cardinals, you fall back on the law of trichotomy. It is A if B is less than or equal to A. It is B if A is less than. The higher fellow wins always. The larger cardinal wins, and he simply ignores the other fellow's contribution. Right? If I can close the door and say, if the professor and the student jointly write the paper, professor gets the Shanti Swarupa award. Student gets ignored. Okay, nobody heard it. Okay. Similarly, if you multiply, the higher fellow survives the same result. It is A if A is bigger, A to B. The bigger fellow survive always. Okay. A to B is. That's very peculiar. And A plus A is A. Whenever you have infinite cardinals. For infinite cardinals, A plus A will be equal to A. So things go oddly with infinite cardinals. In the sense that ordinary arithmetic works for a while, and it also fails in certain situations. So the arithmetic of infinity, one has to be fairly careful. And many of the proofs are tricky. They involve, some of them are easy, and particular cases are easy. General cases are more difficult. They involve much more than what we have done so far. Some of the things I will come back again if you use those. If you want a good look at some of these things, not probably, if you want to look at a full detail, probably a better book which is more difficult book to read in all its grandeur, still not all in its grandeur, but reasonably good, is Hewitt and Stromberg. Real and abstract analysis. I had a professor, you know more, by name Caspar Goffman, whose book also I am going to give a reference. Goffman used to joke about this book, a fantastic book. This book is not for beginners, and an advanced fellow doesn't need it anyway. So that's, you already know analysis. You should know analysis to read this book. But the amount of information in this book is phenomenal. The most abstract results are available. And the other book is Caspar Goffman. Real functions. The earlier chapter, many of these things. And one more book. Then Stromberg himself, classical real analysis. This is a marvelous book. not available. It is out of print, but there is a sneaky download available. If you are clever enough, you can find a sneaky DIV version or something like that, which you can convert to a PDF version if you want. And some version is there, you can get that. Okay, there are lots of such things that are done there. These are 2 or 3 books which you can refer to with respect to some of these set theoretic business. So I don't know what other book I can give. I think the Hewitt and Stromberg will have everything, all these things. Most of the things I said will be there, but all the proofs and things like that, some of them require arithmetic. So what I will do in the next class is head towards the so-called axiom of choice and well-ordering theorem, okay? And make certain common figures, which is one of the most, just like the continuum hypothesis, the axiom of choice is one of these. And one of the equivalent versions of that, namely the Zorn's lemma, is one that is repeatedly used, and that will come in one of the proofs here, okay? Many of the proofs here. So the next class will be well-ordering theorem, partially ordered set, well-ordered set, well-ordering theorem, axiom of choice, the next few classes. And that should be all that I will cover in set theory for the time being. Okay.